Number 19 gives us a Taylor series about x equals 5 for a certain function f converges to f of x for all x in the interval of convergence. The nth derivative is given by this formula, and f of 5 is 1/2. So again, we've seen this a lot of times. It feels like at least every other problem. Write a Taylor polynomial for f about 5. So they didn't tell us to give the first couple of terms. They said write a third degree Taylor polynomial. So I'm going to build it first. F of x is approximately equal to f of 5 plus f prime of 5 times x minus 5 plus f double prime of 5 times x minus 5 squared over 2 factorial plus f triple prime of 5 times x minus 5 to the third over 3 factorial. And now we need to plug in some numbers. So f of x is approximately equal to 1/2. That was given. Plus, so when we plug in 1 for f prime, we don't get plus, we get minus. So we get negative 1 to the first over 1 times 1 factorial over 2 times 1 plus 2 is 3. And we still have this x minus 5 up here. When we plug in 2, we get plus 2 factorial x minus 5 squared over 2 to the second times 2 plus 2. And when we plug in 3, we get minus 3 factorial times x minus 5 to the third over 2 to the third times, oh, I forgot an extra little 2 factorial down here. Sorry, don't forget that guy. Times 2 to the third times 3 plus 2 is 5 times 3 factorial. So the factorials are going to cancel. Might as well not write those. But I don't have to for my final answer. So I guess I'll clean it up. So I've got 1/2 over minus x minus 5 over 6 plus, you don't have to do this, x minus 5 squared over 4 times 4 is 16 minus x minus 5 to the third over 8 times 5 is 40. I'll just leave it like that. Okay, so for part B, find the radius of convergence. So we need some sort of an nth term. So this is kind of nice to have this pattern here. But remember, you can always go back to the default of like, what is that nth term? It's going to be the nth derivative at 5 times x minus 5 to the n over n factorial. And that's going to be negative 1 to the n times n factorial times x minus 5 to the n over 2 to the n times n plus 2 times n factorial. So the n factorials will cancel. And then when I'm doing my ratio test, I ignore the alternating piece. So the limit as n approaches infinity of the absolute value of x minus 5 to the n plus 1 over 2 to the n plus 1 times n plus 3 multiplied by 2 to the n times n plus 2 over x minus 5 to the n. Let's rewrite this with things that have canceled. So on the x's, we have x minus 5 left. There's a 2 in the denominator. The n plus 2 on top stays. The n plus 3 on bottom stays. But it's a tie, so we're left with the absolute value of x minus 5 over 2. That converges by the ratio test. I guess I could have done, well, no, yeah, ratio test because of the n plus 2. Converges by ratio test if negative 1 is less than x minus 5 over 2, which is less than 1. And to get the radius, I multiply the 2 out. You isolate the x minus c. So the radius of convergence is 2. This didn't ask for intervals, so I'm not going to bother checking the endpoints. And then part C says, show that the sixth degree Taylor polynomial for f about 5 approximates f of 6 with error less than 1 over 1,000. So if we use a sixth degree Taylor polynomial, we need to find R6 of, what do we approximate f of 6. That should be less than or equal to the seventh derivative at z, and z is just something between 5 and 6, times 6 minus 5 to the 7th over 7 factorial. Right? Let's see what the seventh derivative comes out to. So the seventh derivative at z would be, let's see, should we be doing our first neglected term? No, I don't think so. We've got the seventh derivative at z. So because because we were here, we could say, well, that's going to be, less than or equal to, if I put in 7, 7 factorial, because I don't need the negative 1 to the n, over 2 to the 7th times 7 plus 2. Now that's the derivative at 5. That's the only information I have to go off of. So I'm going to use that. Or I could probably do alternating series test as well, because these terms are alternating. But either way, you're going to be finding like the next neglected term. So I'm just going to go with this. And then this is 1 to the 7th, so I don't really need that. 7 factorial. So those cancel out. We're supposed to show that this is less than 1 over 1,000. So we've just got to do this work. 2 to the 7th times 9. We just need to show that that's a bigger denominator than 1,000. So 2 to the 7th, go with the 2 that you know. Like I know 2 to the 5th is 32. That means 2 to the 6th is 64. That means 2 to the 7th, I'm doubling that, is 128. And 128 times 9, get out some of our old-fashioned multiplying skills here. So 18 plus 7 is 25. 9 times 1, 1,152. So 1 over 1,152 is definitely less than 1 over 1,000. So I'm just showing the Lagrange form of the error. It didn't matter where the center was because you're not actually plugging an x into this formula. This formula just uses the number of the derivative, so we're okay there. All right, that was the last odd problem in the packet.